It's a great pleasure for me to introduce today's speaker, Dr. Bruce Anderson from Boston University, where he is in the Department of Earth and Environmental Sciences. So Bruce Anderson did his undergraduate work in physics at University of California in Santa Barbara. Then for his PhD, he went to Scripps Institute of Oceanography, also in California, where although he's by training an oceanographer, but he did his PhD research on regional climate modeling in North America using NOAA's data model. And he has then he was a NOAA research associate for 1 year at MIT and for 1 year at University of Hawaii before joining the faculty at Boston University, where he is now an associate professor. And so Bruce Anderson has published extensively on regional climate in precipitation variation in different regions of the U.S., the summer in the North American monsoon, climate in the eastern U.S., and so on. And he has published also on ocean-atmosphere interactions, and a very interesting piece of work which he has published recently actually gives an alternate explanation for how ENSO events come about. And that is, which he will explain in his seminar today. It is by fluctuations of the trade winds. So let us welcome Bruce Anderson.
We'll see if I speak too loud or too quiet. I'm not used to microphones. I haven't taught a 101 course in quite a while, so I'm not quite used to yelling. We'll see. Can everybody hear me in the back? Volume's okay? Okay, well, first of all, thank you for having me down here. Not quite the first speaker that I know of. I think I'm the second, but hopefully I'll keep the ball rolling and keep you guys entertained at least through lunch. And so, as was mentioned, what we'll be talking about in today's seminar is the El Nino Southern Oscillation, which I hope you're all familiar with, so I'm only going to give a very basic primer on it. But what we want to talk about is these El Nino and La Nina events and the onset induced by extratropical circulations in the atmosphere. I think everybody has this reigning paradigm, which isn't incorrect, that a lot of the variability in the El Nino Southern Oscillation is intrinsic to the tropical Pacific. And what we want to try and emphasize is there might be other mechanisms for triggering the onset of these events. And the one I'm going to be talking about is the trade wind charging mechanism, which is newly named, but it's always, I found, good to have a name. It helps you get some recognition. This thing has been on the books for 10 years or so, but now we have a name and it helps, I think. So we have a name, that's the important thing. I'll actually try and actually describe what that name means to you as we go along. It's not just a bunch of words. So what are we talking about? I think you guys know that there is this thing called the El Nino Southern Oscillation, which represents a change in the state of the equatorial Pacific Ocean and atmosphere. People care about it because in changing the state of the equatorial Pacific, we can actually produce a large-scale boundary condition forcing of the overlying atmosphere that in turn produces variations in the atmospheric circulations and climate around the world. So just as a basic primer, as I said, what is the El Nino Southern Oscillation? It's a change in the state of the equatorial Pacific and ocean and atmosphere. So here is one of the sets of diagrams I like to use. Why? Because it shows the actual state, not the anomalies, not the variations that accompany the El Nino or La Nina or the Southern Oscillation, but the actual state of the system. So over here we have South America, over here we have Indonesia. We know that there tends to be easterly trade winds that blow from east to west. That induces a movement of warm surface waters to the western Pacific, that in turn produces the western equatorial warm pool, so a piling up of warm water over here. In addition, because of the surface water divergence over here, we need some replacement water. It comes from below, so we have upwelling of cooler waters from below. That sustains the cooling in the eastern equatorial Pacific. So now we're having this temperature gradient between the eastern equatorial Pacific and the western equatorial Pacific that induces a change in the overlying sea level pressures. In fact, produces a pressure gradient force that helps sustain the trade winds. I think you guys are all familiar with this. Now, a few of the things, though, that I also want to highlight are not just the horizontal circulations, but the vertical circulations. We're well aware that when we have the warm water here in the western equatorial Pacific, that's the region of instability, very strong convection. That's where we get a lot of our precipitation. But in addition, we have variations in the subsurface temperatures, or the subsurface state of the ocean. When we start piling up the warm water over here on the western equatorial Pacific, that in turn produces a depression in the thermocline. And so the thermocline, you're probably all aware of, is that very narrow region between the warm surface waters and the cooler abyssal waters. Okay? And so this starts to depress as we push all this water over to the western equatorial Pacific. Conversely, as we lift the thermocline, or as we produce upwelling over here in the eastern equatorial Pacific, we bring that thermocline and the cooler waters below it closer to the surface. That's what's inducing the cooling of the eastern equatorial Pacific. So there's your basic state. Now, the reason I like this figure, it shows the conditions during an El Nino, which represents a warming of the surface waters in the eastern equatorial Pacific. Recognize, though, that these waters are not warmer than these waters. They're just warmer than they normally would be. Okay, that's the first thing I want to highlight. So what happens as you warm these eastern equatorial Pacific waters? Well, you reduce the temperature gradient, hence you reduce the sea level pressure gradient in the overlying atmosphere. That in turn reduces the pressure gradient between the eastern and western equatorial Pacific, and the trade winds start to slacken. The one thing wrong with this figure, you'll see it all the time in textbooks, is that these arrows shouldn't necessarily be pointing in the reverse direction. It's not that the trade winds are reversing, they'll almost never reverse, but they are weakening. Okay? As soon as you start to reduce the trade winds, all the warm water that you had piled up over here starts to slump back across the equatorial Pacific. As this water is removed from the western equatorial Pacific, the thermocline up here starts to shoal. But in addition, now that you have less surface water divergence over here in the eastern equatorial Pacific, you don't have as much need for the upwelling from below, and you start to have the thermoclines here slump down and remove the cold water storage from the surface. As you do so, you produce less cooling, this region warms up even more, you've got your positive feedback, and the system moves towards a full-blown El Nino. Okay? I won't talk so much, well, I'll talk about it briefly. As this warm water surges back across the equatorial Pacific, that in turn moves the sources of convection, and indeed you start to induce convection all along the Pacific, reducing it over Indonesia. Okay, so those are the variations that accompany the change in the state of the equatorial Pacific during an El Nino. Okay, so there's my basic primer. One of the things I wanted to highlight, though, in bringing this up was that while we talked about the initiation of this El Nino as a warming of surface waters over here, that very rarely is your first signature of an onset of ENSO, or onset of an El Nino. Turns out that one of the predominant precursors to an El Nino event does not occur in the surface, but actually occurs in the subsurface. It's an initial change in the thermocline depth in the equatorial Pacific that is one of the best known precursors to El Nino events. And what you end up having is a depression in the thermocline, effectively a trough. It's a trough along this density gradient on the thermocline, and that trough can propagate as a wave along the thermocline towards the eastern equatorial Pacific. Effectively, as that trough approaches the eastern equatorial Pacific, it lowers the thermocline away from the surface waters. That removes the cold water source from the surface here in the eastern equatorial Pacific, allowing these waters to warm up. That's the initiation of the onset of an El Nino. Okay? So keep in mind the role that the subsurface temperatures play in initiating that, the onset of ENSO, because that's going to be key as we go forward, okay, for this mechanism that I'm about to introduce. Okay? So we have our El Nino Southern Oscillation. You probably have seen it this way. This is the anomalies or the variations in temperature that accompany an El Nino. This indeed is the El Nino for the winter of 2010. Here, reds represent warmer than normal waters, blues represent cooler than normal waters. This is the archetypical view of how people see the El Nino or its inverse La Nina. But just realize that these are variations in temperature. These are not warmer temperatures than here, they're just warmer than they normally were. And that's why I like the previous figure. So if you ever have to give an El Nino talk, those are the ones I actually like to present. Okay, so Now, why do we care about the El Nino Southern Oscillation? Because we know it modifies not just local, but also regional and global atmospheric dynamics. And just to sort of capture your attention, I'll focus on the 2010 event. At least in our latitudes, how does it do it? Very simplified view. I'm going to admit that right up front. But during normal conditions, in boreal winter particularly, and almost everything I'll talk about focuses on boreal winter, we have two jet streams. High latitude, upper troposphere, narrow jets of winds. The one I want to focus on is the subtropical jet stream during boreal winter, usually transecting northwestern US, southwestern Canada. But we know that the jet stream is the boundary along which synoptic storms form, mid-latitude cyclones, and so the jet stream itself becomes the storm track, and this is where the storms tend to track into. As we warm the equatorial Pacific, we modify the tropical circulations. In fact, we modify them so much that we can induce a variation in the jet stream such that we shift the subtropical jet stream south and we actually intensify it. Okay? And what does this do? It produces a change in climate by changing the storminess a particular region experiences. Regions either end up experiencing more or less storminess during a given year and hence have variations in their climatological temperature and precipitation patterns for that year. And so I'll just highlight a set of storms. This is a storm that hit California during the 2010 year, January 2010. It's a singular storm. It's not an El Nino storm. It wasn't induced by the El Nino. It would have been there anyways. The real question is, where did it track? And it tracked a very different location than you might expect under normal conditions. And to see that, let's step back. Here is an infrared image for a single day, January 22nd. This is that storm we just saw. It's actually transected California and hitting the southwestern US. But indeed, that storm was preceded a couple of days earlier by that storm, which was preceded a couple of days earlier by that storm, and is subsequently going to be followed by that storm. So indeed, what we ended up having is storm after storm after storm after storm tracking across here. And then what did they do? Well, during really strong El Ninos, the jet stream strengthens enough that these get shunted out over the Atlantic and start to dissipate. 2010, relatively standard, not strong El Nino. That's right about here is where the jet stream started to turn. Anybody here for 2010? What was it called? Snowmageddon. This was the Snowmageddon year of 2010, where each of these storms tracked across the southern US and then just shifted north and went right up the eastern seaboard and dropped snowstorm after snowstorm after snowstorm on you guys. We got a bit of it, but Maryland, DC, and you guys were the ones that got really hit. And so what do we see? We see a climatological signature of this change in the storm tracks, such that during the winter of 2010, all of these regions experienced more than average precipitation, and that continued all the way up the eastern seaboard to you guys right here. Okay? So that was what drove the Snowmageddon for that year. Anybody know what was happening? Oops, I forgot this one doesn't allow me to, let's actually go to the next slide. Oh. Hey, don't freeze on me. That's a shame. I've never had that happen. Let's see if we can play here. Okay, please, there we go. So there's not only climate implications for the US with wetter than normal conditions down here. Anybody know what was going on in 2010 up here? Winter of 2010?
Drought.
Well, drought, what did it affect? There was a sporting event that year. That was the Winter Olympics. If anybody follows the Winter Olympics, they had a heck of a time putting on a Winter Olympics up here. Because they weren't getting any snow, all the storms were down here, and as this shows, it was actually much warmer, and they couldn't even make snow. So they were trying to put on a Winter Olympics this year, which is exactly the wrong year to be doing it. Granted, they chose that year about a decade before or something, but the wrong year to be holding an Olympics up here, or at least a Winter Olympics. As opposed, well, not as opposed, but in addition to North America, South America, Indonesia, Australia, even parts of Europe are all affected by this change in the state of the equatorial Pacific associated with the El Nino Southern Oscillation. So that is why we care about it. So for that reason, people have spent enormous amounts of time investigating what kickstarts these El Nino Southern Oscillation events, and then how does the system evolve over the next coming months so that we might have some predictability of these events. Now, while I said most people consider the El Nino Southern Oscillation to be a variation in the intrinsic characteristics of the tropical Pacific and the coupling between the ocean and the atmosphere therein, there is indications that the El Nino events and La Nina events could be influenced by extratropical atmospheric circulations up to a year in advance. Okay, so about 12 months prior to a full-blown El Nino, we see signatures in the extratropical Pacific that could serve as initiators for these events. Okay? Now, this has been something I've looked at, other people have looked at. Most people who have looked at this have investigated how these extratropical variations in the North Pacific influence the air-sea interactions over the tropical Pacific. How does the ocean atmosphere interact with one another, and how can those changes in those interactions modify the state of the equatorial Pacific? We're actually going to look at something else. Indeed, very few of the research has looked at how these extratropical circulations impact the subsurface temperatures of the equatorial Pacific, despite the fact that we know it's these subsurface temperature changes that are a key initiator of ENSO events. Okay? And so that's what we're going to delve into, and that's what that says. And indeed, what we hope we find, and I think we have found, is that there isn't a much more direct pathway for these extratropical circulation features to influence the state of the equatorial Pacific without having to worry about the complexities of air-sea coupling or air-sea interaction. It's actually just a direct forcing of the equatorial Pacific that then evolves on its own accord into a full-blown ENSO. Okay? So, let's get started. Now, what are these extratropical circulations? Well, this is one way to represent them. There are various ways to identify this. You can do it by asking, well, what's the leading mode of covariability between sea level pressures or upper air wind fields and the state of the equatorial Pacific 1 year later? You could ask, what is the leading mode of non-ENSO related variability in the atmosphere? And it turns out that that pattern tends to precede ENSO events. The easiest way, which I've done 12 years after I started this, was just to come up with some metric for the state of the ENSO. It's not my metric, it's a metric. It's the area average temperatures between 170 west and 120 west, 5 north and 5 south. It's a standard metric for the state of the equatorial Pacific. Take that metric and correlate it with sea level pressures 1 year earlier. That's all you have to do to get this map. And this again is all boreal winter. What is the state of the boreal winter ENSO, and how does it relate to the state of the atmosphere 1 year earlier? Okay? Well, this is what you get. In sea level pressures, this is an actual regression, so these are actual values in hectopascals. There we go, it works. I have to remember that I have to switch hands. You get this dipole structure. Prior to a warm event, that would be a positive value of the Nino 3.4, you tend to see a weakening of sea level pressures over Hawaii and a strengthening of the sea level pressures in the Aleutian Low region. So you have this dipole anomaly. It's actually called the North Pacific Oscillation. Again, I didn't give it that name. It was named that in the 1930s, but it is the analog to the North Atlantic Oscillation. Okay? Now, accompanying those changes in sea level pressure, and the significant values are outlined in the contours there and there, we have a change in the wind fields. As we reduce the sea level pressures here, this is the anomalous wind stress fields. The accompanying of what you're actually doing is reducing the strength of the northeasterly trades. And that's what these arrows represent. And again, only the significant variations are shown. So we end up reducing the strength of the Central Pacific trade winds. We also see some association with wind fields over the western and central equatorial Pacific, and that'll come into play later on. Okay? So those are the anomalies that accompany or that precede variations in boreal winter ENSO events by 1 year. Now, we can actually create an index for this, and the easiest way to do that is to find the largest correlation values and take an area average of the sea level pressures over that region. You'll notice it encompasses Hawaii. Originally, we called this the sea level pressure index because I was being really creative that day. Since then, just for clarification, we now refer to it as the Hawaii Sea Level Pressure Index, or in the next figure you'll see it as the Hawaii NPO, because it's the Hawaiian lobe of the North Pacific Oscillation. And we can just find how the year-to-year variations in that index compare with year-to-year variations in the state of the ENSO 1 year later. And not surprisingly, by construction, they're well correlated. Here are the year-to-year variations in the Nino 3.4 index. Here are the year-to-year variations in the Hawaiian Sea Level Pressure Index. And by construction, because that's how I constructed it, they're well correlated. The correlations are surprisingly high. At a 12-month lead, minus 0.58, there really isn't anything that beats this, okay? It's really hard to predict the ENSO 6 months out, difficult to do it 9 months out, really difficult to do it 12 months out. Again, this is artificial because I constructed it to have the highest correlation I possibly could, but that is what we're finding. Is there is this very good correspondence between what's happening over Hawaii in the sea level pressure fields and what's happening to the state of ENSO next year, okay? Now, I'm going to shift gears a little bit, and instead of asking, well, what conditions precede the state of the El Nino Southern Oscillation, I'm going to ask what conditions occur concurrent with the North Pacific Oscillation. So we're now going to change our focus a little bit. We're going to ask, if we have variations in the sea level pressures over Hawaii, what does the state of the Pacific, both in the extratropics but also in the tropics, look like? Okay? So that's where I'm headed. So if we do that, it's a busy figure. I'm going to spend a couple of minutes explaining it because you're going to see it in time series form in just a second. This is a composite for the January-February mean fields for years in which we have lower than average sea level pressures over this Hawaiian region. Okay, so it's a composite in the low pressure anomaly years for the sea level pressure index. First of all, what do we see? And these are anomalies. Well, again, where is it? There it is, yeah, zonal winds. The wind fields, or the anomalous wind fields, are seen here. Not surprisingly, accompanying a lower than normal pressure here is a weakening of the trade winds, and as you'd expect, there's also these signatures in the equatorial Pacific. For future reference, in the next set of figures, instead of showing all the vectors, I'm actually going to just show the outline of the significant zonal wind anomalies. So that's the white contours. Anywhere you see a white contour, underneath that is where the zonal wind anomalies are significantly different from their average value. Okay? And solid lines mean it's a westerly zonal wind anomaly. I mean, the anomalies are moving this way. Dashed lines are an easterly zonal wind anomaly. Okay? So we expect that there's this weakening of the trade winds. Now, what's in the black contours? It's the variations in sea surface temperature. As we reduce the trade wind fields, what we actually end up doing is reducing the surface heat fluxes. We reduce the amount of evaporation that occurs. That, in turn, allows the water beneath the zonal wind, or the trade wind anomalies, to warm up. And that's the solid contours here. So we see this warming of the surface temperatures extending from the western equatorial Pacific up through the tropical Pacific, and it actually gets up to here, up into the subtropical Pacific. So you have this band of warm water anomalies beneath the region where the zonal wind, or the trade winds, are weakening. Okay? And if anybody's familiar with the literature, this is a signature of either the seasonal footprinting mechanism or what's now called the meridional mode mechanism. That we'll talk about that in just a little bit, but that sea surface temperature signature is exactly what you'd expect given the weakening of the trades and the establishment of either the meridional mode mechanism or what's called the seasonal footprinting mechanism. And I'll get to those later. Okay? So people know about those. What they hadn't looked at is what's shaded. That's why I shaded it, because I wanted your eye to be drawn to it. That is some signature of what the subsurface temperatures are doing. It is the vertically integrated or vertically averaged temperatures from the surface to about 300 meters down. Well, not about, to 300 meters down. So it's some measure of what the temperature structure in the subsurface looks like. And it's not the surface temperature signature because you can see that there's no overlap here, for instance, with the surface temperature anomalies. So what we see is, accompanying this weakening of sea level pressures over Hawaii and the weakening of the off-equatorial trades, we are actually establishing this massive volume of warm water in the subsurface, extending from about 180 degrees west to about 135 degrees west, 5 degrees north to 5 degrees south. Okay? And we do see some of the heat content, or what I'll refer to as warm water volume or heat content, or just temperature, subsurface temperature anomalies along the equator. But if you can see it, this dark red here indicates that the largest anomalies are actually in the off-equatorial region. That's where we're seeing the largest signature of subsurface heating accompanying the decrease in sea level pressures over here. Okay? So now what we're going to talk about is how this,
What's the contour for the shading?
the shading is, all of these are significant. It turns out, just to make sure that they're all applied on the same, they're all normalized. So it's 0.4, 0.5, 0.6, 0.7, 0.8. They're all by, just like this, 0.4, 0.5, 0.6, 0.7, 0.8. So it's 0.4 standard deviations, 0.5 standard deviations, 0.6 standard deviations, up to almost 1 standard deviation, 0.8 standard deviations. So for the number of years that go into this composite, it turns out that 0.44 is the 90% significance interval. So that's what I show in the white contour. That's what I show here. I didn't feel like showing the 0.44 and then the 0.5, so I just showed the 0.4 there. But yeah, those are the intervals. But the most significant anomalies in that sense are the ones right through here. Does that help? Yeah, okay. So now what I want to do is, this is sort of the end of boreal winter condition, seasonal mean. How did we get to this point? So now what we're going to do is walk through time. So here are the 30-day mean fields, exactly plotted as before, now removing the wind vectors and only showing the zonal wind anomaly contours, for 30-day means centered on the given dates. Okay? So again, composited on years in which we have lower than normal sea level pressures over this region. So what do we first see? Well, we see initially some weakening of the trade winds associated with that white contour. Beneath that, a warming of the surface waters, and maybe some indication of a warming of the subsurface waters, but not much. Get about through midway through your boreal winter, we have a continued weakening of the trades. We continue to warm the surface waters, but now we have an indication that something's going on in the subsurface, both in the equatorial region, but again, the largest signature is in this off-equatorial region, just to the south of the zonal wind anomalies themselves, and that becomes important. Okay? Go forward another 2 months, middle of February, middle of March, so end of boreal winter effectively. What are we seeing? Well, all of these fields have been amplifying, they've been getting stronger. The sea surface temperature anomalies have been getting stronger, but now we've established this really large subsurface temperature anomaly, again, extending from, if you can see the longitudes, 180 to 120, 5 degrees north to 5 degrees south. And now it's becoming much more symmetric about the equator. Although, again, the largest anomalies are just to the south in the off-equatorial region there. Now, if you're, again, familiar with the literature, I want to point out another interesting feature. And that has to do with the meridional mode. So I mentioned that when people have talked about lowering of sea level pressures here, they've talked about changes in air-sea interaction that could accompany it, that could then influence the state of the equatorial Pacific. The main way they explain that is through this meridional mode mechanism. And what that means is that you expect, notice for instance here, to the south of the sea surface temperature anomalies, you see zonal wind stress anomalies, okay? A weakening of the trades. Well, you then expect the next time period to see the sea surface temperature anomalies migrate southward. Accompanying that, you would expect the overlying sea level pressures to decrease. And in turn, because the sea level pressure anomalies are migrating equatorward, the wind stress fields would also migrate equatorward because they would be at the southern flank of those sea level pressure anomalies. And so you would expect the whole set of patterns to migrate equatorward. In fact, that was the expectation, that this sea level SST anomaly would migrate equatorward, eventually reach the equatorial Pacific over here, and kickstart a positive El Nino event. But that's not what we're seeing. These fields are staying relatively stationary through this whole time period. They're just fixed in that off-equatorial or tropical region. They're not migrating southward as you might expect. Okay? So then we start to charge the whole equatorial Pacific, or increase the warm water volume in the equatorial Pacific. Now let's go another 2 months forward. So again, all the anomalies are intensifying. Again, we're not seeing this equatorward migration of the sea surface temperature anomalies. Instead, what we're seeing is an eastward propagation of the subsurface temperature anomalies, such that by the end of May, what you're getting is subsurface temperature anomalies that are extending all the way across the equatorial Pacific. And as they do so, it turns out that they're moving along a thermocline and shoaling in the eastern equatorial Pacific. And if I had June up here, what you'd see is even larger SST anomalies here, but they're starting to influence the sea surface temperature anomalies from below. Okay, you're not getting this equatorward migration of sea surface temperature anomalies, you're getting a warming from below in this case. So we've generated this very large volume of warm water in the equatorial Pacific that is subsequently migrating or translating eastward and eventually shoaling and warming this eastern equatorial Pacific surface temperatures such that that can then jumpstart the El Nino. Okay? So that's the process whereby we think that subsurface temperature anomalies are influencing the state of the equatorial Pacific enough to generate an El Nino event. Okay? Now, I will highlight all of this is from the observationally constrained data. All the atmospheric variables are from a reanalysis, ECMWF's reanalysis of the atmosphere. All the ocean data is from a reanalysis of the ocean state. I get an observationally constrained estimate of what the ocean state looks like during these years. What I will get to is the model, a simulation of this in a second. But that's what the observations are telling us. Just to highlight, we're going to take a transect across here, 135 to 150 west. And I'll only look at the seasonal mean fields for right now. But where do these subsurface temperatures reside? I've been talking about this heating of the subsurface temperatures. Where does that reside? And again, these are actual anomalies, again, composited on those years in which the sea level pressure index is below normal. This is depth from 0 to 200 meters. This is latitude from 0 to 15 south and 15 north. The shading is the shading. It is the deviation in temperatures at those depths and those latitudes. What is the gray lines? And again, the black lines show the significant anomalies. What are the gray lines? Those are the climatological isotherms, with relatively warm water near the surface here, cold water here, a very large gradient representative of the thermocline through here. This gray line is the 22 degrees C isotherm line. I'm going to use it throughout as an indicator of the depth of the thermocline. So while we've been seeing anomalies in the vertically integrated temperatures in the previous figures, where are those occurring? They're occurring on the thermocline, okay? And then there's also some other feature I want to highlight is this kidney-like shape here and here. The largest anomalies are not on the equator, they're just off the equator, okay? And as far as the signature of the surface temperature anomalies, it barely shows up. Remember, for this, we expected this equatorward migration of the sea surface temperatures. Well, that's where the sea surface temperatures are confined to, about 10 degrees north, okay? They're just not making it to the equator, okay? Okay, so that is the observationally constrained state of the system during these years in which we have lower than normal sea level pressures. Now the question is, can we explain what's generating this these subsurface temperatures and then what's happening to those subsurface temperatures once they've been generated? And that's where the model came into play. So this one actually has the newest reference, but if you saw, this all started about 10 years ago. Only within the last year or so did we have the modeling capability to simulate this process. We needed a high-resolution model centered on the tropical Pacific. We got one up and running. Now we could actually test our hypothesis, and that's exactly what we're going to do right now. So how do we do it? This one might be difficult to see in the back. What we did is we asked ourselves, what are the anomalous wind stress and heat flux forcings that are occurring when we lower sea level pressures over Hawaii? So if Hawaii is there, the vectors are the anomalous sea level wind stress fields that accompany that, and so a weakening of the trades here, but also a change in the equatorial winds in the western Pacific and the eastern Pacific there. The contours are the anomalous heat flux anomalies, anomalous heat flux fields that accompany that weakening of the trades. So a warming of the temperatures in the red regions, sea surface temperatures there, a cooling of the sea surface temperatures in the blue. So then what we did is we ran two runs. We ran our control run. We took our ocean-only model, which is from 30 north to 30 south, spanning the tropical Pacific, and forced it only with the climatological wind stress and heat flux fields. So we got a climatological evolution of the ocean, or estimate of the state of the ocean. We then did a ramp up, ramp down experiment, where starting in November, we forced it with just the climatological fields. Then mid-November through December, we ramped up and started to add in incrementally these anomalous fields to our climatological fields. Ran it with the climatological and anomalous fields for this boreal winter, end of March, ramped it back down, and then let the model run of its own accord with no anomalous forcing for the next 2.5 months out through the end of June. Okay? So that's our model run. What we're then going to do is ask ourselves, what's the difference in the state of the equatorial Pacific under the control run versus the experimental run? Okay? Now, let's do it. The easiest way to do this is to actually animate it. Yep, that's the one I want. So you're going to see 2 animations, and if I get through this, I've done enough, at least as far as I'm concerned. You can ask about everything else, but this is what I wanted to make sure I got to. You're going to see 2 animations. The first animation has 2 panels. The top panel is a 3-dimensional image. This is depth here. This is longitude here, or latitude here. This is longitude here, running from Central America, or South America, out to Indonesia. If you see the black lines and blue lines, that is the climatological position of the 22 degrees C isotherm. Again, an indicator of where the thermocline position is. You're going to see 2 blobs form. One is going to be this yellow blob. That is every place within the experimental run that is 0.5 degrees warmer than in the control run. It's the 0.5 degree isothermal surface. The orange blob is everywhere in the experimental run that is 1 degree warmer than the control run. It's the 1.0 degree isothermal surface. Down here, you're going to see a planar map. Once this disappears, South America, Indonesia. The coloring represents the depth of the 0.5 degree isothermal surface. If it's blue, it means that the temperature anomaly is relatively deep, 200 meters down or so. As it becomes progressively red, it means it's shoaling. If it's bright red, it's at the surface. Okay? So, before I start the animation, a few things to look for. Look for the initial subsurface temperature anomalies here in the off-equatorial region, not the equatorial region. You'll see the same thing down here. Halfway through the animation, this is going to rotate to a view from the north so that you can see the east-west propagation of those anomalies along the thermocline, and eventually they're shoaling into the surface.
Excuse me, you might want to turn the light off, that round knob.
Sure. Yep. Better? There we go. Here we go. I'll start it and then I'll stay here just so that I can stop it halfway through. So there's the initial anomalies. There it's rotating. So by about January, we've established this subsurface temperature anomaly initially in the off-equatorial region, but then you get this very symmetric anomaly that spans the equatorial region. Now we're going to view it from the north, and you're going to just watch it propagate along the eastern the equatorial thermocline into the eastern equatorial Pacific and warm the surface temperatures from below. So there's the eastward propagation. By now it's reaching the surface. By now we're shutting off the forcing. At this point we're starting to damp down the forcing, and what we've done is we've charged the subsurface ocean temperatures. That effectively means we've added warm water to our warm water and increased the subsurface temperatures over a very vast expanse. And again, both meridionally and zonally, that stuff is just going to sit there and slowly migrate along the thermocline. So by now we're starting to ramp down the forcing. Now we want to see what the influence of this subsurface temperature anomaly that we've generated has upon the surface temperatures. And so those temperatures continue, the anomalies continue to propagate into the eastern equatorial Pacific. By now, they've reached the surface. In fact, by given the orange color in there, you know that they're starting to warm the surface waters by up to 1 degree. And now this is the end of the simulation. And so again, this is the signature of all the surface heat flux forcing, and absent any RCA interactions, you wouldn't expect it to migrate equatorward. It doesn't. But now what we are seeing is this very strong warming of the subsurface associated with the charging of the warm water volume, of the increase in heat content along the central Pacific. Okay? So So that is the process that we were trying to simulate, or we hypothesized is happening. It appears to actually be happening in our model simulations. Now, it turns out that if you look at the wind fields, though, that we used to force this model with, there are two sets of wind fields that could be important. One was the wind fields over the western equatorial Pacific. Indeed, it's known that if you have wind stress forcing in the western equatorial Pacific, that can modulate the depth of the thermocline in the western equatorial Pacific, which then, as a Kelvin wave, propagates to the eastern equatorial Pacific. That is one forcing mechanism. But there's this other forcing mechanism associated with the off-equatorial winds in the central Pacific. And that is also a possibility for generating this change in warm water volume in the subsurface throughout this region. So what we wanted to do was isolate those two processes. So in fact, we did another set of experiments where we only forced the model with western equatorial Pacific wind stress forcing. And what you're going to see in yellows is all the places in which that isolated experimental run is 0.5 degrees warmer than the control run. We also did the same thing, isolating only the central Pacific wind stress forcing. And those anomalies are going to show up as orange. And then finally, just as a test case, we only forced it with heat flux forcing, no wind stress forcing. Those anomalies are going to show up in blue. They won't show up well at all, but you can ignore them anyways. What we really care about is what's happening in response to the western equatorial Pacific wind stress forcing only, yellow, or central Pacific wind stress forcing only, orange. That's the difference you want to look for in this next animation, okay? And again, initial anomalies will always be in the off-equatorial region, but now you can see how the response of the ocean differs between these two wind stress forcing regions. So the forcing's applied, the anomalies start to develop. What we see is that we are developing a response both to the central Pacific wind stress forcing, but in yellow also the western equatorial wind stress forcing. As time goes on, it turns out that the western equatorial wind stress forcing, through the inducement of this Kelvin wave, a depression of the thermocline that then propagates as a wave to the eastern equatorial Pacific, is actually arriving first. Okay, that's the yellow colors that are arriving here first. So they're now reaching the surface and warming the surface, but we additionally have this large volume of warm water sitting here in the central Pacific, induced solely by the central Pacific wind stress forcing. Right about now, we're starting to turn off our forcing. As we turn off our forcing, the western equatorial Pacific wind stress anomalies start to dissipate, but now we're seeing this slow migration of the central Pacific wind stress-induced anomalies along the thermocline. They're still there, but they're also moving eastward, and you're going to see them slowly augment and replace the western equatorial wind stress-forced anomalies. So again, by the end of the simulation, we have a relative warming of the surface waters as well as at depth, induced principally by now, at this point in time, these subsurface temperature anomalies generated by that central Pacific wind stress forcing. Okay? And that is the signature that I would say is the trade wind charging signature. And we'll talk about, if I have enough time, talk about why I refer to it as trade wind charging in just a little bit. So let's go to this. I just did the animations. We can then ask, well, let's take a transect and look again with depth and with latitude, 15 degrees south to 15 degrees north, the temperature response in our experimental run compared to our control run when all of our forcings are applied, when just the with just the westerly equatorial wind stress forcing is applied, when just the central Pacific wind stress forcing is applied, and the sum of these two, which is this. So this is the full response. Notice that very kidney-shaped, or maybe lung-shaped structure that's centered off the equator. Well, we can ask, is it reproduced by the sum of these two? And for the most part it is. What we miss is the surface heat flux signature here, which is there. But what we see is that this western equatorial Pacific wind stress forcing does produce a response in the temperatures confined mostly to the equatorial Pacific. It's centered on the equatorial Pacific. that the off-equatorial signatures, and actually the horizontal extent that accompanies this change in warm water volume, is almost entirely due to the Central Pacific wind stress forcing. And that when you sum these two together, you really do get an adequate representation of your full response. Okay? Now, in retrospect, it turns out we actually applied a relatively weak forcing to this system. And the reason is that we took all of the years in which the sea level pressures were lower than normal and used that for a compositing index. It turns out that represents, in average, a 0.7 degree standard deviation of the sea level pressure index from its average value. If we instead narrow the range of years which we include, and only include those in which the sea level pressure index is 1 standard deviation or greater from its mean, we can then look at a more strongly forced system, and that's what I'm going to show next. And this is that more strongly forced system, but only in response to the Central Pacific wind stress forcing. And again, these are actual anomalies. I've changed the color bar slightly to match what we saw in the observationally constrained data. So there's our model response to Central Pacific wind stress forcing only. There is the observationally constrained estimate of what should be happening. And the positioning differs slightly, and we're also losing some of the signature here because that's in the observations, we do still retain the influence of the western equatorial wind stress forcing, so that's no longer in our model runs. But there's a surprising correspondence between these two, both in magnitude and structure. Okay? And again, this field here is only in response to the Central Pacific wind stress forcing. So, if you should ask, I will finish in 5 minutes, and you can ask about this figure in the remaining 5 minutes. This is a figure that describes why we call it trade wind charging. It is the meridional mass transport that accompanies the zonal trade wind anomalies. So these are the Central Pacific only wind stress anomaly fields. Those tend to induce a meridional transport. Theoretically, you would expect them to, according to Sverdrup transport balance, that's equatorward in both hemispheres. That's the charging process. We're just jamming a lot of, anomalously jamming a lot of water into the equatorial Pacific. That's depressing the thermocline. That's warming the waters along the thermocline, which is then propagating towards the eastern equatorial Pacific and eventually depressing the thermocline away from the eastern equatorial Pacific and warming the surface waters. That's what we see theoretically. If we calculate the Sverdrup response to the zonal wind stress anomalies, this is what we see in the model. And there's other signatures in here, but the magnitude and even some of the positioning of the meridional mass transport response is nearly identical to just what we'd expect for Sverdrup transport. Okay? And that's the reason we call it the charging mechanism. It's in reference to the recharge-discharge mechanism, if you know the literature. I'll skip this one. So then the question becomes, well, we know that we can generate at the end of June a surface temperature anomaly of a certain magnitude, okay? We can't actually amplify that because our model does not have air-sea interactions. It doesn't have the Bjerknes feedback that can take an initial sea surface temperature anomaly and drive it towards a full-blown El Nino. So we can't actually follow this through till December and say, hey, we have an El Nino, because we don't have the air-sea interactions to sustain that El Nino. What we can do is ask some questions about how those sea surface temperatures compare in our model with what the historical record has. And that's what these two figures show. So what we did is we took an index. We know where the sea surface temperature anomalies bubble up. And maybe I'll show this figure. If you had to focus on a figure, it's this one. This is depth here. This is longitude here. These are the initial surface temperature anomalies that are eventually reaching the eastern equatorial Pacific along the thermocline. And if you see the scale, they're about 1 degree. Okay? It turns out that this region is the Nino 3 region. It's 90 degrees west to 150 degrees west, 5 degrees north to 5 degrees south. So let's take an area average temperature in the Nino 3 region in our model and compare it with the observed evolutions that we've seen historically. So in our model, this black line here is the simulated response in that region. No response at all. 0 response in our experimental run compared to our control run for the first 6 months or so. That's because none of that subsurface temperature anomaly is reaching the surface. By May, June, what we're seeing is there is a warming. It's about 0.45 degrees. If you can't see it, there's a gray line in here that represents the 0.5 degrees C isotherm or anomaly sort of a threshold for when you have a full-blown El Nino. We haven't reached that state by the end of our integration. But there's two things we can compare it to. The first we can do is compare it to the evolution that eventually produced a full-blown El Nino. So these, we go back in our historical record, we find all the full-blown El Ninos, and we track back in time what their Nino 3 index looked like over the previous 12 months. And you can see the further back you go in time, there's a larger spread. Some are relatively strong El Ninos, transition to La Ninas, and eventually bump back up into El Ninos. Some start as very strong La Ninas, and eventually end up over here in El Nino state. But if you take the median value, that's this one right here. And you'll be, right there is our simulated state. Right there is the median state for this evolution that accompanies a transition into an El Nino. So it's the median evolution. And then not surprisingly, the median value translates into an El Nino of about 0.1 degree, or 1 degree Celsius. So the way to phrase this is that the evolution that we're seeing in our simulation is characteristic of one that would develop into an El Nino, okay? The other thing we can ask is, well, will it? And the way we do that is look at analogs. We take a 0.5 degree Celsius window around our simulated value, look for all the historical evolutions that by the end of June had a Nino 3 index value that was within that window. The other characteristic is it had to be increasing through this time period prior. We didn't want any strong El Ninos that were descending through this window to a La Nina. So these are all values that passed through this window that had some increasing trend in their Nino 3 value over the previous 6 months, and then ask where do they end up. Well, here's the median value. The median value does end up as an El Nino. 6 of the 10 do end up as El Ninos. 8 of the 10 tend to be warmer than normal, and only 2 tend to fall back into a La Nina state. So what we're seeing is not only is this characteristic of the evolution that might lead to an El Nino, it's also likely to do so. So while we can't definitively show that this will develop into an El Nino because we don't have the requisite air-sea interactions in our model, there is this evidence from the observation record that they very well not very well, they might translate into La Ninas the following year. Okay, I won't go into the alternate mechanisms because I want to give you time to ask questions, and I won't go into how various indices relate to the state of the El Nino Southern Oscillation 1 year later, because there are other indices other than just this Hawaiian sea level pressure index. But I will just end by saying there does appear to be, both from my work as well as others, evidence that extratropical processes can influence the state of the equatorial Pacific and lead to an El Nino 12 months later, and those circulation features are characteristic of the North Pacific Oscillation. It appears that they do so by charging the warm water volume of the equatorial Pacific through the gradients or the curl in the zonal wind stress. This is the Central Pacific wind stress forcing is generating this warm water volume that can influence the sea surface temperatures in the eastern equatorial Pacific through propagation along the thermocline, and that's what this says here. And eventually, those SST anomalies, which is what the last slide showed, are generated. The ones that are generated are consistent with ones that develop into mature ENSO events, and in fact are likely to do so. And the last phrase is, this is fundamentally different from previous mechanisms because it really focuses on the subsurface temperature response, not the air-sea interactions that accompany those circulations. So with that, I give you 3 minutes. Thank you. Yeah?
I just wanted to ask, does the equatorial undercurrent play a role in affecting the subsurface?
That's the one thing we have not looked at. So we certainly, I can tell you why the subsurface temperatures are generated, and it is a dynamic process. It's not a diabatic process. It's not heating. It's actually changes in both the meridional and vertical circulation. Why does anomalies propagate? Whether it's a zonal propagation infection or whether it's a true wave-like phenomenon, just a oscillating process, that one we're not so sure. We definitely see the temperature anomalies, but whether they're actually being affected, we'd have to go get the phase speed, we'd have to figure out what the density differences are and the expected wave speeds. We haven't done that. That's absolutely correct. It could be either of those two processes.
Yes, but Dr.
How do you get this positive wind stress effective results? I saw the whole thing you talk about in Also quicker.
Thanks, you asked. We'll do it here. Here is the zonal wind stress anomalies, well, in white. And what you end up having is a relative strengthening here and a weakening here. The curl that's associated with that is that way. And so that curl will tend to produce equatorward migration on each side. If you had a traditional ENSO, and this is what threw us for a long time, a traditional ENSO would also have a weakening, but the weakening of the trades, or the easterly winds, would be maximum along the equator and minimized as you go away from the equator, which has a curl in the opposite direction, such that that sense of, well, that structure of weakening of trades has a positive curl. This way. And this one has a negative curl. They're both weakening of easterlies, but the key is not the magnitude, it's the curl that accompanies those weakenings. And this has exactly the opposite curl that you'd expect for an El Nino, i.e. a discharge event. That's why we call it charging, because the charging process is distinct from the process that accompanies an El Nino southern oscillation, because the curl is different. The dynamic response is the same, but the sign of the curl is opposite. And so the process, the response of the thermocline is opposite. This produces a charging, not a discharge. Is that?
Yeah, no, what I'm saying that it's not obvious from the picture there. I guess you didn't plot the other.
Yeah, the one where I would have talked about it more is this one. Here is the positive wind stress anomalies this way, negative wind stress anomalies. You'll see the largest response is not where the wind stress fields are the magnitudes are largest. It's where the gradients are largest, and that's exactly what you'd expect. So it's where the curl or the derivative is.
What is the question?
Yeah.
Let me try. Yeah. So you're in your conclusion, you're saying that it's sort of an equator mass flux. Is it really an equator mass flux, or is it just the weakening of the divergence? Because you have the.
Well, actually,
Repeat the question for the
yeah. So the question is, are we actually producing an anomalous mass flux?
No.
Or are we just weakening the climatological situation? It turns out, I'll half answer it. The way I'll half answer it is, if you look at the anomalous circulations that accompany us, or even think about the wind fields that we're looking at, this is actually, while you're weakening the trades, you're actually strengthening the climatological curl in this region. Because if you look at the climatological wind stress fields, strong easterlies here, weak easterlies here, strong easterlies here. So the natural gradient in this region is this way, or the curl in the climatological conditions is this way. You are then augmenting that with these fields. So while you're weakening the trades, you're actually strengthening the curl. What you end up doing is strengthening the meridional tropical cell circulation that's found in this location. So there is a tropical cell circulation that's confined to the first 200 meters. This process is actually amplifying that. And that's actually one of the reasons this is the thermocline, climatological thermocline position. The tropic signature of the climatological tropical cell is a depression here, lifting here, but also a lifting here. Well, what do we see? Where are the temperature anomalies? Warmer here, colder here. We're depressing this even further. We're lifting this even higher. So we're actually augmenting the oceanic circulation, even though we're weakening the off-equatorial trade winds. That's because we're augmenting the curl itself, which is the climatological feature that's driving all of that.
So we have a question. Please.
You showed the SAP index and the Nino index is highly correlated.
Yep.
So how does your trade wind charging mechanism works in La Nina year?
Well, if it was all linear, it would just be reversed. It would effectively, if it was all linear, I should have gone the other way. If it was all linear, you'd take all these signs, you'd multiply them by -1, you'd intensify the trade wind activity, but you'd intensify it in the negative direction, or you'd intensify it in the off-equatorial region. What that would end up doing is producing a curl that would tend to discharge water from the equatorial Pacific, lifting the thermocline. So effectively, by enhancing the trade winds, you're going to lift the thermocline. As you lift the thermocline, then you're going to generate a cold water volume or cool water anomaly that will then propagate to the eastern equatorial Pacific and cool. That's effectively a crest that's coming closer to the surface, cooling the surface waters even more, and then generating a La Nina. That's all if it's linear. Now, there are processes that are nonlinear that are associated with, for instance, advection, where that process might be either enhanced or weakened during El Niños or La Niña events. But linearly, it should all work in reverse.
So Vic Liu has a question.
Also for this correlation, does that SST in Nino 3.4 includes the major phase of the El Nino, which is when the El Nino is major, when you do the correlation?
Yeah, let's go to the sea surface temperatures, which is the next slide. Nino 3.4 is from here to here. So if you were to ask, do we have an El Nino during the same years that or a La Nina during the same years that we're having this change in sea level pressure over here? The answer is no. There is no metric across the eastern equatorial Pacific, the Nino 3.4, the Nino 3, the Nino 1.2, that is correlated with this sea level pressure index. Now, that doesn't mean the tropical Pacific can't influence it. There is some thought that maybe by warming the western equatorial Pacific, this is producing a tropical cell in the atmosphere, an enhancement of the tropical or a reduction of the tropical cell circulation that is influencing these sea level pressure indices.
Well, actually, my question is about, well, your mechanism is about the trigger of El Nino.
Yeah.
Well, from this relation, it seems to me it also includes the major phase of the El Nino.
If you want to call it the trans-Nino phase, the phase between an El Nino and La Nina, it does look somewhat like this. But whether that represents a true dynamic mechanism of the El Nino itself is another question. Is that phase transition really a dynamic process? Is it a real dynamic oscillation? This is really the question. Is the El Nino Southern Oscillation really an oscillation? In which case, this would be a dynamic phase period of phase transition within an oscillatory behavior. Or is it just two modes that are bumping up and down that can then be forced towards one state or another? And you're getting at exactly the question that's bedeviled the ENSO community for the last 20 years.
Marvin?
To what extent is the North Pacific Oscillation correlated with these so-called annular modes?
Annular modes. Ooh,
So there is a signal of the angular mode in the North Pacific, near the elution lobe.
So if you were to, so the NPO is, if you were to do it, the second leading mode of extratropical variability in sea level pressures in the North Pacific. That's how you discovered it in you didn't, but in 1932. What's the leading mode of variability? It's the elution lobe. It's just a monopole that pumps up and down like this. Now, how do they relate to the annular mode? I'm not going to answer that. What they are related to is the East Asian jet. So what's happening to the East Asian jet? Either, if it moves north or south, that will tend to produce this dipole structure. If it intensifies, that'll produce your monopole structure. So the surface circulations are related to upper tropospheric circulations. Generally, they're related to what's happening to the East Asian jet, which might be influenced by the Arctic oscillation or the annular oscillation. But I haven't actually looked at that in a regression sense. But they're definitely related to what's happening in the upper troposphere that's then imprinting the signature either on a dipole or, in the case of the North Pacific Oscillation, a monopole in the elution lobe region.
So this is all good using
Thank
the
you.
charging, and how does this compare with the air-sea interaction of driving the give weight?
Oh, I know. Either supposed to be a proposal or a paper, so don't steal it. So we can go at and look, now we have a long enough reanalysis record to ask ourselves, how do well-known modes of precursor variations compare with the state of the ENSO over subsets of time? And so we can find traditional precursor patterns. One is western equatorial wind stress anomalies. One is Hawaiian sea level pressure wind stress, or sea level pressures. And another is SSTs in this typical seasonal footprinting or meridional mode region. And we can ask, how do those correlate with Nino 3.4 the following year over various 30-year periods? And that's this figure. So each of these dots is a 30-year running correlation centered on these years. There's a bunch of them. They're continuous, but that's what they are. This is the running correlation of the Hawaiian sea level pressure index. Throughout this entire reanalysis period, it has a good correlation with Nino 3.4 through the whole period. This is the confidence interval. Anything above this, it's significant. This is the meridional mode SST. So you can see through the first period of the reanalysis, it actually didn't relate to El Nino at all. Only recently, in the period that people were studying, did it. So that's why it came to the fore, but if you go back in time, it might not be a precursor all periods, all times, if you get what I mean. But this sea level pressure index really does seem to be a precursor throughout the entire period. And then the Western Equatorial Pacific wind stress forcing is this one, relatively weak until, again, about the mid-80s, and then it's become actually more prominent than the sea level pressure. So it might take precedence now, but it didn't necessarily take precedence previously. Does that get to your question?
So I think we can, it's getting 1:15 and we can have more questions during lunch, which today will be in the Okubo room. So let us thank our speaker, Dr. Bruce Anderson, for such a good
Okay, so I broke your microphone. Oh, I think I broke your microphone. Just pulled through. Hello? Okay, good. No, somebody left this needle down. Sorry about that. I get a little animated when I talk, so. 30, I'll see all the people. It's early in the semester. I haven't gotten burned out yet. I did a great job. This is, yeah, if I could get this kind of